everyone. My name is Courtney Hughes, and I'm so excited to host what's going to be an amazing session, a perfect primer to our Trailblazer with Neil deGrasse Tyson happening in just a few hours. And I'm sure that everyone here is familiar with MIT, the Massachusetts Institute of Technology, one of the most respected universities in the world. Within the MIT ecosystem is the Media Lab. It's a research laboratory which focuses not only on creating and commercializing transformational future technologies, but also on their potential to impact society for good. The MIT Media Lab has embarked on a new expedition that reimagines humanity's return to the moon, and as a member of the MIT community, Dell Technologies is taking part. This February, MIT launched its first lunar landing mission since the Apollo era, sending 3 payloads to the moon's south polar region. MIT's base was Lunar, a mission control space designed by the MIT Department of Architecture, students and faculty in collaboration with the MIT Space Exploration Initiative. The installation, which featured Dell AI PCs and other infrastructure components, allowed visitors to observe payload operators at work and interact with the software that's used for the mission, thanks to AI and real-time 3D data visualization. And we are so fortunate to have with us today 3 visionaries that play very critical roles, in the To the Moon and Stay program. First is Kim Slater, Chief of Staff to the MIT Media Lab. Kim is a seasoned aerospace engineer and space program leader with over 15 years of experience supporting NASA missions and developing flight systems for the Space Shuttle and International Space Station. Prior to her current role as a Chief of Staff at the MIT Media Lab, she led Draper's Space Innovations Division, spearheading technical programs that integrated commercial spaceflight, climate applications, and social impact initiatives. Kim, thank you so much for joining us today.
Thanks for having me.
Also joining us is Dr. Dawn D. Haddad, a research scientist at NASA Ames in the MIT Media Lab Space Exploration Initiative. Dawn leads lunar imaging and software systems for the resource camera on the MAP lunar rover, the first US-made commercial rover to land on the moon in March of this year. With a PhD from MIT in Media Arts and Science, Dawn's work blends planetary science, robotics, and immersive computing, developing tools for real-time 3D terrain modeling and spectral imaging and hybrid virtual environments for exploration. Dawn, it is such an honor to have you with us today.
Oh, thank you, Courtney. It's a great honor to being here.
Yes, and working very closely with both Kim and Dawn on the To the Moon project from Dell is Martin Sawtell. So excited to have you here with us, Martin. He is the XR lead within Dell's CTO office, where he explores use cases, technology platforms, and implications of compute in virtual physical spaces. Martin's work focuses on exploring the developments in physical AI, visual representation, and XR wearables. Thank you for joining us, Martin. Now, before we jump in, all of you have the opportunity to ask our panel questions via the DTW app, and they will be available immediately following today's session to tell you more about the mission and to show you more of this amazing research at work. So I think we should go ahead and dig on in. Kim, I'd really like to start with you. Why the focus on space at the Media Lab?
Such a good question. I mean, I've spent my whole career in space, so for me, it's just,
super
I
cool.
mean, how can we not? I think if you look at the Media Lab, part of our vision is everything we do is by, with, and for all. Everything includes humanity, includes people. We design things, but we design them for humanity. And there's something about space that always sort of inspires us to think about the outer bounds of what we know. There's sort of, if you say we're going to talk about space today, I'm pretty sure you're all already interested before I've even opened my mouth.
Yes.
Because space is exciting to all of us because there's still so much to learn. So there's that pioneering spirit in all of us where we just want to learn more, and space is one of the most exciting ways we do that.
I mean, and why is it important for science and society?
Why is it important? I think as a human race, we've always been focused on what we don't know and learning more.
Yes.
A lot of the technologies developed in space are really more focused on on making life here on Earth better. A lot of the remote sensing imagery improves the way we live here on Earth, but it also goes back to that sentiment of what don't we know, and as pioneers, how do we learn more about improving the world around us?
Yes, I've always been fascinated with space too.
See?
Yes, I'm one of those, the moment you say space, I'm
it
just
just
like, ooh, I'm
happens.
coming.
Yeah, yeah.
And how and why do you work with companies like Dell to ensure that this work has impact?
Yeah. So the Media Lab is a really special place at MIT. Everyone loves the word interdisciplinary, but we've been living interdisciplinary since our incarnation 40 years ago. We literally put biologists and engineers and artists and musicians physically in lab spaces together to create, because we recognize that the world's biggest challenges need the best minds and the most creative minds. Another thing we do is work very closely with industry. Dell is one of our partners and one of our industry members, so that we don't become an echo chamber. We could all sit in a corner and just talk about physics for the rest of our lives, or space, or biology, but by staying tied in with companies like Dell, it helps us focus on the real world challenges and not kind of invent our own. Yeah, we're thrilled to work with Dell. We think of the lab too as sort of, Da Vinci had it nailed, where there was art and music and water and design, and Leonardo da Vinci did all of those things. So we'd like to think that if Da Vinci had a Dell, we'd probably already be living on the moon. We'd be traveling, we'd have a trip to Mars on the weekends.
Yeah.
So it keeps us better.
I like that, Dawn. My next question is for you. Tell us more about the To the Moon to Stay program.
Oh yeah, absolutely. And a little bit before telling you about this program per se, I would like to just mention that MIT as a whole was part of a mission, a historic mission with the Apollo program. And now we're coming back, and we came back to the moon since the 60s. And this is a little bit fitting under the Artemis program, which is Apollo's twin sister. And part of the Artemis program is pushing the industry back to be part of these space endeavors, to basically decentralize the process of space exploration, where it's not just governmental agencies such as NASA being part of that, but NASA working with the industry to be pushing humanity back into space. And the moon is our first playground, as they say, to establish this sustainable human-robotic presence. And part of these endeavors is our work done on the To the Moon to Stay program, part of the MIT Media Lab Space Exploration Initiative, also in collaboration with NASA Ames. We did send 3 payloads to the moon. They landed on March 6th, and that was part of the Intuitive Machine IM-2 mission. But what took us there to the moon isn't just IM-2, but also a company known as called Lunar Outpost, and they developed the first US-made rover to touch down on lunar surface. And on board of that rover, we actually sent a micro-rover.
Oh, wow.
So that was the kind of an interesting concept, inspired by Star Wars, where you have, these robotic swarms that will come to fix a bigger spacecraft. But then we wanted to send a couple of them, and this is the other part of why space, because in space, the limitation turns into a creative, to harness the creativity of researchers and scientists. We wanted to send a swarm of these robotics, but we were only able to send 1 unit. Also, it's really expensive to send, payloads to the moon. But this is also part of developing the first lunar economy. Mm-hmm. So that's what also interests the industry in being part of that. We also do a lot of testing on these payloads in zero gravity flights. But we also sometimes do our testing through analog missions.
Yeah.
The other payloads that we sent, it's inspired by Voyager, the Golden Disk, and I'm sure our audience here is quite familiar with the Golden Disk. But this is such a miniature version of a Golden Disk. It's etched in a nano-wafer. And what's taken there is human poetry with these waveforms that you're seeing etched into the nano silicon wafer, and with poetry from every single spoken human language telling us poetry about the moon and what it represents to our culture.
I do have a question for you. You mentioned payloads, right?
Right.
So tell us more about payloads and what they're designed to discover.
Right. So payloads are very important, and maybe Kim, would you like to tell us more about that since you?
Sure. We say, we have our own language. Engineers have our own language, space engineers and then we have acronyms built within acronyms, and we just assume you all understand. Payloads are just scientific research that we fly in space. So it used to cost tens and hundreds of millions of dollars to fly things in space. We had to go through NASA. Now with so many accessible commercial space launch companies and vehicles, students are able for thousands of dollars to build and fly things. So this is a perfect example. Don mentioned how MIT was part of the first lunar landing in the 60s with the Apollo missions. And now with just this tiny little chip, we were able to bring the voices of so many in more than 50 spoken languages?
Yes.
I forget, every spoken language, hundreds, to the moon. And so now they're there.
Yeah.
So that's sort of a really interesting way to think about to the moon to stay. We're not just going back this time to put footprints and plant flags. We're going back to build a station, to explore further, to have access to get to Mars from there.
Yeah.
And we've already landed with those beautiful voices on the moon.
Yeah. So Don, what would you say is
There's also two types of payloads. You have active payloads and passive payloads. And this is an example of a passive payload. The robotic unit was an active payload. And the last payload that we sent was on board of the MAP rover. As you can see here, it's a modified version of a time-of-flight imaging system that we worked with NASA Ames on space hardening that device, because it was commercially available off the shelf, but then undergo a lot of that vibration testing, thermal testing, shielding, because the environment of space is such a difficult environment to navigate, not alone to send payloads to. And what it does, it's a, and this is, by the way, the MAP rover by Lunar Outpost in a rendering. We also work with simulation environments. We worked with, for instance, the NVIDIA Omniverse simulation environment. But what we're seeing here on the screen is the MAP rover by Lunar Outpost and a beautiful rendering of a lunar simulation environment. And this is our camera. What this camera does, and the way we worked with it is to blend the canvas of space exploration and science. On one side, it's used to do 3D reconstruction, and we are quite familiar with that technology today, whether it's done through LiDAR systems or it's embedded on our phones today. But also with time-of-flight imaging, we were able to do 3D reconstruction and data visualization on top of that. So the idea was to create digital twins of lunar environments. This is one side of the research. The other side is that the way time-of-flight imaging works through this system, it relies also on near-infrared. So, you have the spectrum of light. You have the visible, you have the invisible. Near-infrared imaging, and specifically on this device, is at 850 nanometer. We cannot see it, but this is definitely and very useful to be able to tell us information about the soil. And in that specific case, the regolith on the moon. And the biggest goal, going back to why this is important for us, is permafrost on the moon.
Yeah.
And this is presented in what's called the permanently shadowed regions, PSRs. These locations were never hit by sunlight, and they still preserve that water ice that is very important to sustain human presence. That's why we're going back to the moon, and specifically the South Pole region. And then what do we do with this data? We visualize it. We also, for example, what we're seeing here on the screen is a 3D reconstruction of the NASA Ames lunar test bed. This is where we went to test our imaging system. And you could access this online as well. And there's plenty more information about this. If you go to the tothemoon.mit.edu website, you can learn more about our payloads and about this endeavor.
That's super cool. So Don and Martin, I know that MIT and Dell worked hand in hand on this project, right? How did this collaboration work from a technical perspective?
Sure. So as members of the Media Lab, we have the opportunity to not only access or view your research, but to work with you. So when we had this opportunity come up, it was a great time to bring the toolbox. We build infrastructure, we build tools, and that's what you guys need to do your work here, right? That's just the beginning. So when we bring those tools, there's elements of the Dell AI Factory which are being put down, and Dell Pro Studio. And that could be precision workstations in this case, AI PC as well. So with those, we're able to work with the other element of our network, our partners, NVIDIA, in the case of Omniverse and AI Workbench, to implement and visualize, tools and pipelines to begin to see this data. And this is actually a render that I did, Don, with one of the workstations where I 10x the point cloud count using some visual effects tools to give a really prescient view of what that would be. And we'll get into where that goes creatively in a moment. So Don, anything to add about that discovery process of what we can do with these?
Yes, absolutely. Part of working with digital twin environments and simulation tools is that you could fail safe and you could fail ahead of time and you could train AI algorithms within these environments. Our devices and through what we have here is also fits into perception in general and perception engineering, which is actually a very important topic with any robotic unit, any robotic system that we want to send, to space for localization, for and mapping. They call it SLAM, positioning. But this is one part of the project. The other part is how to use AI to upscale. But then there's a very thin definition between using that for immersion and presence versus science. As for scientific experiments, and this is something we have explored with NASA, we can't really rely on AI synthetic data to perform any science, but they really favored using that for astronauts training and other applications.
So I should interject and just mention that Don, when he does the 3D scene reconstruction, yeah, you can take the native image. Each pixel has a depth value, so you push it back, it's now in 3D. But if you do an Ezra-GAN up-res on that first, now you've got a much higher resolution environment.
Right.
There's a little bit of synthetic data added on there, but the utility for training is definitely there.
And yeah, going back to the limitation and why we did that and what kind of limitation we had in this research project and lunar exploration, we were limited with the data volume and bandwidth that we could actually use to download these 3D scans. And therefore, we developed our own 3D compression algorithm that relies on compressing 2D images and sending that back to Earth, and then we do the 3D reconstruction. And then we apply this upscale on that data. So imagine with just a file that ranges just below a megabyte, we could end up with a 1 gigabyte reconstruction with a very high definition reconstruction of distant environments. And I could talk a lot about that. And I can tell you more about limitations, the Galileo mission, when can go on with how human ingenuity was harnessed through failures and through limitations. And yes, finally, I'd like to also tell you about one outcome and several of the outcomes that we had from the mission. We were able to operate for about 10 hours because we had an off-nominal mission. So in space exploration, lunar missions, you have 3 types of outcomes, right? A crash or a total failure, a nominal mission where you have a percentage of success, mostly towards 100% success, and you have off-nominal missions where instead of operating for 2 weeks, which was the expected, best result, we had 10 hours to operate and test. We tested our communication. We tested a lot of different things. Other companies that were on board of IM2 also had the chance to test their payload. So we had some positive outcome from that. And this beautiful image taken from the Athena lander as it's resting in a crater near Mons Mouton. This is the location. As you could see here on the screen, it's a panoramic image, so we could actually see it in 360, and you could see our beautiful planet highlighted there.
If I could add to that.
Yes.
A lot of what Don and Martin are talking about are taking 2D imagery and making it better. A lot of the imagery of the moon is from the Lunar Reconnaissance Orbiter, so it's from up high looking down. So imagine early Google Maps. The images came from space, but if you look down at the moon, a circle could be a mountain or a molehill, or it could be a tunnel, or you have no idea, it's just a black dot.
Right.
So this gets some imagery on the ground that gives you some of that 3D sense, and all of that bolsters the AI and all of the image mapping they're doing to recreate 3D models so that when other vehicles, autonomous or not, people or robotic landings get there, they know whether they're landing on like a little slope or a big hill. And that blue dot, the most iconic image from space when the Apollo astronauts took an image of Earth from the moon.
Yeah.
That image of Earth we all love just gives us all perspective. So how thrilling that our students were able to do this and look back at Earth and realize, you know, there are no boundaries when you look at Earth. We're all one. It's just a spectacular accomplishment. So
thank you. I'm honored, and it's a big team. But also to add on that, remote sensing can tell us a lot about, you know, distant planets and in that case our moon. But then we need to get down to the centimeter resolution, because with remote sensing at its best, we get 1 meter per pixel type resolution. That's why we need to go down to the 1 centimeter and below to be able to really use the in situ resource utilization, and that's what would really drive the sustainability of human presence on
I mean, this is just so amazing and very groundbreaking, and I would love to hear from all of you on what did we learn from the mission in March, and like what's next. So Kim, I'd like to start with you.
What did we learn and what's next? I know we only have a few minutes left, so I will say we learn what we learn every time, is that spaceflight's hard. Nobody gets into this because it's easy. You know, it's that famous JFK quote from the Rice University where he said, we're going to the moon not because it's easy, but because it's hard. I actually like the line that came after that, and I'm going to butcher it. I can't remember it verbatim, but it's something about because these goals help us organize the best of our abilities and skills. And so every time we have a mission, fully 100% successful, off nominal or not, I think this is where we learn more. The next one's going to be better. So we've learned we can land on the moon and take imagery. That's on the South Pole, which is super hard to get to too, has the most information about that water ice. And water ice breaks apart into not just water to build a human presence, but hydrogen and oxygen, when you break them apart, are what you use for rocket fuel.
Yes.
To help us get further. So that's what next. We're going back. We're going back to stay, and then that'll help us launch into Mars and further to keep learning more.
Oh, I love it.
And we're here at a great event at Dell Tech World. And it's worth mentioning that our mission control was also built. So, you know, this mission was also brought a lot of MIT departments together. And the Department of Architecture helped us build this beautiful shell of a mission control. But on the inside of it, we actually use Dell Technology, and you know, a big shout out to Ken Glass and his team from Dell for providing and working with the Media Lab as a member for providing the equipment. And on one of those machines, I still have it at the lab. On March 6th, we were able to send a command to the moon. So that's on its own was a small success, but a big success for our team. At the MIT Media Lab to be able to send a command to the moon at 10:30 p.m.
So, Dell's, I saw the nod.
He's looking like my turn. Yes, it is.
I'll wrap it up on my end. So, Dell's mission is to drive human progress through the power of technology. And this is a great example in a figurative sense of how we can do that. But if you think about space and all of those unknowns that we can now begin to explore, it stimulates a sense of curiosity that we've all had since we were a kid. It's natural when you think about space, and Neil's talk this afternoon will definitely go there too. But the other part of it that I've been discovering over the last year or two is how much my curiosity is stimulated by AI. These tools help you ask questions, sure, they can answer some of them, but more importantly, they accelerate not just the ideation process in that respect, the kinds of things that we want to try, whether we want to get multi-angle captures and reconstruct an object and then make it a Gaussian splat, you can do that now. It's not a huge, you know, the amount of work you need to do is not going to get in the way as much as before. It's accelerating things in that regard. So that's what I'm most excited about. And we've got a demo here today as well. It's back over there near the wooden wall. You're all invited. We have an Astro Ant, and we can do some live image capture with Regulus simulants.
Yeah, right. We actually have Regulus simulants. They did not come from the moon, but they're an analog, and you could get to see what could look like as a water ice permafrost analog. We actually use dried up salt, to perform that analog. And this is on the surface, but there's also the different payloads actually we're testing underneath the surface, deep into the regolith, the presence of water ice. So, and these are the big questions. And how AI and collaboration tools would play a big role into that. For instance, we developed our Lunar mission control had an AI agent embedded in it. So you could actually ask it questions as we are feeding it with incoming data from the mission, just to have this human AI connection as an agent built into a virtual environment. So yes, we love working with splats and Gaussian splats and all type of modern techniques to do reconstruction in general. And yes.
I do have a question before we open up for Q&A. Reminder, you can submit them through like the Dell app as far as the questions. So while they get those questions in, Dawn, you had mentioned it, like AI, right? And the console and what was built. Why are collaborations like this so important when we think about the potential of AI? I mean, even what it's doing today right now.
Yes, I mean, as we're moving from machine learning and deep learning, from data analysis and back all the way into agenetic AI, and that's a big topic that we're hearing a lot about today, digital twins. We started working on digital twins back in 2014, and now that it's coming back into the ethos, we could see how AI is playing a bigger role, not only in our digital life, but also in our physical environment. And as these agents transition from, and we saw the demo of an agent earlier today, as that is transitioning from a digital life into a physical environment and physical work through a robotics, you could only imagine how that could drive space exploration in the future. And imagine you could be just like tapping into a swarm of robotics from Earth through virtual reality and other platforms, but you're also connected through AI. And once you're not there, they're NPCs. They're like non-player characters, and they're driving themselves. They're excavating, and then you could tap into one of these units and just like immerse yourself remotely. So, big dreams, big goals, and we hope to get there soon.
Yeah. I'd like to say too, just these collaborations are so important. I mentioned before how without industry, not just for the tools, but keeping us focused on what the real challenges are, we wouldn't be able to accomplish what we accomplish. But this makes us do it, like Don mentioned, at an accelerated speed. I would even venture to say that your young daughter will be able to buy a ticket to the moon in her lifetime. I mean, we're not that far off. We're putting our next big Artemis mission with NASA, will land the first woman on the moon. And to stay, not to just leave a footprint, but to start building a space station there.
Yeah.
So all of these tools lead to, although they're robotic and AI, more human exploration too.
Yeah. Martin?
Yeah, and through that creative process of discovery that we're talking about now, we're learning as Dell how people like Media Lab, how people in the future that want to visit the moon virtually, how would they be using these tools? And they're valuable insights for the CTO organization because we use that to map out the future, to discover these new use cases and optimize for that. So that's a great aspect of the collaboration on the Dell side.
I do have one question that came in. What are you most excited about with this partnership and all that you're going to accomplish and do?
I want to stand in VR on the moon. But with actual data. That'd be sweet.
Yeah.
Don?
I'm excited to go back to the moon virtually and through robotics, absolutely. I love being in mission control personally, and I love to interact with robots at a distance. So more missions, more data, more payloads, hopefully in the future.
And Kim?
I think it's not just the robotics and all of the technology that gets us there and gets people back there. For me, the exciting things are, I have no idea what is coming next. That if we sit here again in 5 years, we'll think back to what we know now. And with AI and all of these tools, it's accelerating so quickly, we can't predict what we'll discover and what our students will create in the coming years.
Oh, it's so great. Kim, Don, Martin, thank you all so much for sharing this amazing story with us. And thanks to our audience for joining today's discussion Our panel is going to be available for additional questions or to show you more of the exciting research. I hope you all have a great rest of your time here at DTW.
Thank you, Courtney.